Welcome, Boris.
Thank you. All right. All right. Okay, so some of you may not be familiar with Enfabrica. We've been around since 2020. And we are a semiconductor company, a networking company. Our first product is called Accelerated Compute Fabric, or ACF. And we like to add a little S at the end for a super NIC. I know it's a mouthful, so let's try to understand what it is. It's actually a highly aggregated device that combines capabilities and features of your typical PCI CXL switch, an array of RDMA NICs, and an Ethernet level 2, level 3 switch in one device. And what it allows us is to basically streamline communication across PCI domain, across CXL domain, and across networking domain in a very seamless and very optimized way. So if you look, obviously it's much more complex than this, but the three main components are a PCI Express switch with 160 lanes of PCI Express Gen 5, a number of NICs or DMA engines, and a 3.2 terabit per second Ethernet switch. So in addition to all those impressive numbers, we support a flexible software-defined transport. So you can run standard RDMA over Ethernet or OKV2, or you can run kind of modified flavor of RDMA. All this is possible. Now, tomorrow, Shijit will talk about different applications and capabilities of this device and what can be done. In this talk, I'm focusing on a specific application, memory aggregation. So, as I mentioned, part of the capabilities is CXL support. So we can actually connect up to 9 CXL devices or CXL controllers, PCI Express Gen 5 by 16, in sort of one domain and one appliance. And we are actually showing this this box here in the room. So in the break, I invite everybody to stop by and take a look. What does it do actually? So imagine a lot of memory aggregated together. Today, I think the devices available on the market, you can get a CXL card with 512 gig memory. This technology is moving forward. So very soon, there will be 1 terabyte and 2 terabyte devices available. And all this memory is aggregated together, presented to sort of external world as just one memory space. And it's accessible over RDMA at 3.2 terabit per second. So the memory bandwidth is pretty much matched with the networking bandwidth to create fully non-blocking sort of solution. All right. So why shared memory? Obviously, in today's AI world, I know this crowd is more focused on high-performance computing. memory is very important. The computations, again, specifically in AI world, in inference side of things, the amount of data being generated is really immense, and your GPU memory and even your host memory may not be enough to hold all this data. So you can solve it by, adding kind of dedicated memory to specific systems, in which case part of this memory most of the time will be underutilized. If the memory is shared, you can utilize this memory in a much more efficient way. Giving more memory to whatever system, whatever agent that needs it at this point, and dynamically reallocating later on. Now, once again, in case of our solution, this memory is accessible through the network with a very kind of fast, very fat pipe, 3.2 terabit per second. So you will never get to a point where you have all this memory and you want to use it, but you have to go through, let's say, one RDMA NIC at 400 or even 800 gigabit per second to get to it. All right, so TAME system. So we've built this device, this silicon. It's quite large. Again, I encourage everybody to stop by it and take a look. Now, how do you actually connect it to devices that need to be connected? So we built this appliance we call TAME's box, which basically exposes all those PCI slots. Over here, you can see all the networking ports. So it's 4 OSFP ports, each port running at 800 gigabit per second. And here, all the 10 PCI Express slots by 16. It's very versatile appliance. You can plug your GPUs, you can plug other devices. In case of a memory appliance, we fully populate this box with CXL memory cards. All right. So we've created a system that we called Emphasis. That stands for an Elastic AI Memory Fabric System. Now, the sort of uniqueness or the beauty of this solution is that it's completely decoupled from your server architecture, right, or your GPU architecture. Typically, if you need to add memory to a system, let's say you need to add CXL memory to a GPU system, right? So first of all, this server needs to be built in such a way that it allows any kind of expansion. You need a CPU or GPU, whatever, to support CXL protocol, right? And even if you have all that, you probably have very limited space to add those additional capabilities. With the shared sort of appliance that is basically connected to your RDMA network, you can add it to any environment, right? So it can be placed as a top of the rack box, connected to your GPU RDMA network, and any GPU can access it. Now, I'm not sure if I mentioned, the access latency is quite low. It's around 6 microsecond, and I'm talking about read latency all the way to the memory and back. And if you compare to maybe other solutions around this space using flash storage, this is probably about 2 orders of magnitude better. And later on, we'll show our initial performance results, and you will see what difference it makes. In terms of cost savings, it's also quite dramatic. If you compare to GPU memory, which is obviously the most efficient, but the most expensive HBM, it's about 5 times cheaper. All right, and maybe last but not least, maybe I will go back to this picture. All this memory is basically managed by a single processor, and it's not a super powerful processor. If you try to create something similar with the standard components, we will probably need an array, I don't know, 4 pretty powerful CPU cores to get to that kind of density. Now, we've shown sort of a top of the rack box, right? You can create entire memory fabric using those appliances. And in this case, we use Enfabrica systems both as sort of initiators. And here I remind everybody the super NIC capability of this system. So those blue cables here, those are PCI cables coming off the servers. Obviously, that requires those servers to be able to sort of take PCI outside of the box, and we have some ideas how you can actually achieve that. And then using, again, RDMA NIC or array of RDMA NICs capabilities of this device, you take out all those Ethernet connections and bring them into a different rack where your actual memory appliances are placed. So now you can serve a number of racks full of GPU servers, all connected to an array of memory through a single RDMA hop. If you need to grow beyond that, just use your standard Ethernet switches, and then the scale is pretty much unlimited. All right. So why is it interesting? Why is it important? Typically, again, as I mentioned, if you run an inference workload, with the number of users, the latency starts to build up. Why the latency builds up? Part of the reason the KV cache starts to grow, and at some point the GPU memory and then the CPU memory is not sufficient to hold the KV cache. If that memory is not sufficient, GPUs will have to recalculate KV cache on every next query, every next iteration, and that's where the latency, the response time starts to grow. So you can, if your server allows, you can add usually it's one CXL device inside the server. That could be your level 3 memory that sort of allows you to go a little further in terms of how many users you can serve, right? But ultimately, you will need a lot more memory, and that's where this shared memory pool comes into play. Based on the simulations we've done some time ago, we've seen that the with the shared memory, you are able to serve much more users, or sustain a lot more queries per second, keeping the both median and worst case tail latency, tail response time under the accepted threshold. And in this case, this threshold is 1 second, right? So you want your responses, you want your AI to respond to your query not slower than 1 second, right? So with this solution, you are able to satisfy those requirements while serving more users concurrently. All right, so that was a simulation. Now we decided to actually build a system and show and measure those performance metrics on the real hardware. So we've taken an open source VLLM framework, augmented with another open source framework called LM Cache. And we've built a setup with this Thames box, with this appliance, populated with CXL memory, and connected several servers as initiators or as clients, basically running those inference workloads. Now, in order to actually glue this all together, we've developed our own what we called RMEM, remote memory layer, that follows kind of standard server client model. So our appliance runs MEMD server. All the client systems run MEMD client. And as I will show in the next slide, this memory layer follows a kind of RDMA semantics with the same mindset, same arguments, but it exposes much simpler key value API to the application, and it makes it much easier to plug in to a framework like an LM Cache, which we've done. So your software stack looks something like that. It would be standard RDMA stack all the way up to here. If you use Enfabrica device as your initiator, you will need Enfabrica Rocky Neck driver, but otherwise, this is your standard RDMA stack. Right on top of that is RMEM layer, and then a little sort of glue plugin to connect it to LM Cache, and then VLLM framework. I'm showing just a snippet of the API function calls available in this RMEM layer. So you can see that it's quite sort of intuitive. Client initialization, opening the pool, opening, closing the pool, and then put block and get block operations that basically, as I said, require a key and a scatter-gather list pointing to the value. All right, so we have assembled the system. And these are the pictures. You can see kind of our early bring-up stages. So this is our kind of test board with our chip on it, right? But on the right-hand side, it's something that actually more assembles the actual system. All right, so we started from measuring just raw performance. How does this memory pool perform? Okay, and we've run, in this case, it's just 2 clients accessing a memory pool with 2 CXL devices over 2 links of 400 gigabit Ethernet. So, and this, as I mentioned here, this data is very preliminary. A lot of the optimizations are still to be done. But even here, we already see that this system actually scales, and it scales very nicely, So we get with the get operations, we get we see over close to 700 gigabit per second throughput, which is not yet closer to 800 gigabit sort of goal, but we're getting there, right? And what is more important, it clearly exceeds your single 400 gigabit link sort of limitation, both on the PCI side and on the network side. Okay, so we've measured our memory pool. It performs reasonably well. Let's try to actually run some inference and see what we get. So we've run a number of experiments, and again, these are very early experiments. So we're going to do a lot more optimizations and study it much deeper and much closer. But from the initial data, we already see some very interesting trends. So let's understand those charts. So a blue line is no cache. So it's a GPU using its own HBM. And in this case, we limit the HBM to 43 gigabyte. So we have 20 users running queries concurrently, but those are relatively short queries with only 3 iterations each, right? So initial question, then 3 more, subsequent questions for each user. So with no cache, the response time basically, and this TTFT is time to first token. It's a very common metric for inference. It basically grows linearly with the number of queries. The next one is local disk. So in this case, the KV cache is basically offload to local SSD. So you will see that after initial, when the KV cache gets generated for the first query, for the next one, it actually goes down. And then it goes up a little bit and kind of goes down, but it stays here around 0.4 seconds. So some improvement, not enough. With the shared memory pool, we see much better results, right? Same trend, but the response time goes down much further. Why? Because the access time, memory pool, even though it's RDMA hop away, its response time is much better than the flash. And then the green line is the local DRAM. So if you have enough local DRAM, you probably don't need anything. But again, there's so much data you can fit in your local CPU DRAM. All right, and then, so this is the time to first token, and this is the generation time, which is basically how long does it take to generate complete response. And the trend is pretty much the same. No cache is the worst. Local disk gives some improvement, then the memory pool, and then local DRAM is, we can say, marginally better in this case. All right, so this is a slightly different workload. We're still running inference, but in this case, the queries are much more complex and much longer in terms of number of iterations, right? So we run 10 concurrent users, but each user stays in the conversation for 26 iterations, and all of that is happening in parallel. So what we see here in the data, because the number of users is smaller, KV cache is building up gradually, as opposed to kind of this bursty explosion when you have 20 users doing this concurrent work. In this case, the KV cache grows gradually. And initially, we see very good response times. You know, then on this scale, it's hard to even see the difference until we get to around 60,000 cumulative tokens served. Then, you know, your no cache test starts showing some fatigue, right, and starts slowing down. All right, so with the local disk and the memory pool, that happens around 80,000 tokens, but still you see some slowdown. Now, what is interesting, again, the orange line is the memory pool, is that when each resource kind of got exhausted and can no longer provide this relief, memory pool actually stays at a certain level and doesn't continue to go up. And in this case, it's basically all about capacity, right? Memory pool has a lot more capacity, so it can sustain this workload for much longer. All right, so conclusions. Again, maybe it's a little too early to draw conclusions because we just started those experiments, but what we already see is that shared memory has a lot of potential, can bring real value specifically to those environments where you generate a lot of data and you need to share this data across multiple compute elements. What we did not touch upon is the fact that when you serve a lot of users and they start their conversation, they ask you, queries, and then let's say pause for some time and then return in a sort of legacy in a standard situation, the next query you would prefer to serve on the same server where you already have the context, where your KV cache is kept, whether it's in GPU memory or a local CPU DRAM, right? And if you can do that, then you'll probably have to either, if you spawn, you need to kind of continue serving on a different GPU, you will either need to recalculate your KV cache, or you'll have to kind of pull it from that remote memory, which may not be as efficient or as quick. If your KV cache lives in this large shared memory pool, that is again 1 RDMA hop away, it may be or will be faster to do that, and it basically creates a new possibility of decoupling your GPU from actual context. So you can use any GPU for any task, and it opens up much better opportunities for scheduling your workload and keeping your GPUs sort of busy and load balanced. Now, we've talked about inference, specific example inference workloads and using memory pool for KV cache offload. There are other ways to utilize this shared memory, either to keep the model data, encodings, intermediate storage for reinforced learning, and more, right? For many of many of the people in this room and on WebEx, doing research around MPI, HPC, we believe there's an opportunity to utilize this solution in all those different use cases and different environments, and that brings me to my last slide. We invite you to collaborate. If you think that this solution is interesting and can be valuable for the work you're doing, we'll be happy to talk to you and see how we can move forward together. Any questions?
So we have some time for questions.
Yes.
I do have a question. So for currently, so for prefueling and decoding separate disaggregate serving environment, how the data KV cache will moves from the prefueling cluster to the serving, to the decoding cluster. Is it directly go to the shared memory pool, or it goes through the HBM memory? Yeah, and a second related question will be is it only works for a single TP or as per parallel group, or it is a memory pool across the entire or larger multiple groups?
Right. So at the end, you've seen, maybe let me go back to where we started. Here. This is the device, right? And this is the concept, right? You don't see pre-fill, decode, so this is the memory appliance with a lot of memory and RDMA access. How you utilize it, it's entirely up to you. What we've done here, and this is just a study that we've put together in a very short time is we took an open source inference framework, VLLM, with an open source KV cache sort of management engine, LM cache, and put it together and ran it to see what benefits we can get from that memory pool. Now, to answer your first question, pre-fill decode. So you will generate your KV cache, you will load it to this memory pool, you will use it later in the decode phase. How do you choose to implement it? That's entirely up to you or whoever develops this solution, right? It can go straight to the memory pool, or it can follow sort of this tiered memory paradigm where you try to keep all your sort of hot data closer to you, and this memory pool serves as L4, L5 memory. There are pros and cons, and it's a little outside of the scope of what we are what we are able to do as a semiconductor company.
Any more questions?
Yes.
Can you hear me? Okay. On the CXL memory fabric appliance picture, you are rocking the front. I was curious why CXL behind it. Won't just the normal memory be okay?
This one.
This one, yes.
Yes. So how do you connect normal memory, right? You need a memory controller, right?
All right, so you don't have DDR on there, okay.
Sorry?
No DDR on ACFS, it's just a PCIe.
Well, it does have a DDR for its own embedded, processor, but it's just one channel or two channels. But yeah, you don't get that kind of density. Yes.
Which company's CXL memories did you populate in your system?
Yeah, so you can take a look in the break. We for those experiments we used smart modular CXL memory cards. What actual DIMMs, I'm not even sure, but they use multiple vendors. Smart modular, so they are a vendor for actual CXL cards, and they use CXL controllers from Microchip and Astera Labs on those devices. Yes.
In this picture, do you support the GPUs initiating CXL memory transactions that then get transported over the fabric, or is it just an RDMA access to the memory expander pool?
Right. So CXL memory is virtualized, right? So it's actually homed to this local CPU that is attached to our device, and it's all part of this system. Outside of the box, it's all RDMA. And again, as I mentioned, we added the software layer that abstracts it even further to just simple key value API.
As far as I know, the state-of-the-art systems for KV cache storage are Mooncake and LM cache. You know the Mooncake system?
Yes.
So why did you choose the LM cache over Mooncake for integrating your CXL-based KV cache store? the uh,
No particular reason. I think we needed to start somewhere, and we looked at Helium Cache first. We might and probably will, try other frameworks like Mooncake, for example. We looked at NVIDIA Dynamo framework. Again, haven't done much yet, but yeah, this is all in front of us.
and to publish this result in some paper in the academia?
Push.
If you want, you can walk over here and use this one.
Anyway, maybe. Yes, if we have time.
How about this one? Okay, this one's better. This isn't really research, right? I mean, the point here is we are a semiconductor company. This is a box. The software is what we use to make this, to show this benefit. We are actually hoping there'll be many people here who will want to run their software, Mooncake, whatever you want, on our box. So it's on you.
Right, yeah.
I really, how to use it? I really love to test this the device slash the box with our own applications. But that said, I'm really wondering, whether you provide some sort of a software layer that we can utilize and, in a form of SDK or some other libraries that I can just simply use with a standard Linux environment. It seems like in your experiment, you have some sort of a ad hoc code to run these KB cache systems.
Absolutely,
But,
yes.
yeah.
All that is part of our software SDK that we will make available to
Do you have any
whoever
diagram
wants to
that
partner
shows
with us.
what that SDK does? I mean, what that SDK includes?
Yeah, absolutely.
It doesn't
That's
show anything in here, so I think.
that's basically this. So all the orange blocks, it's part of our SDK. So if you use this this framework, you wouldn't need to do anything. If you use a different framework, you may need to develop your own plugin at this level, at this layer, to integrate with whatever framework you're using.
Okay.
All right.
Questions from remote attendees?
The one comment I wanted to make, right, in terms of SDK and software integration on this looks just like an RDMA interface. If you look at the API, it looks just like your standard send receive RDMA API. The thing that we've done is actually made it simpler. So you don't have to worry about load balancing. You don't have to worry about striping, all the things, the scaling parameters that Boris was talking about, all that is taken care of. It just looks like an RDMA app. So if you have an app that was using RDMA, its port is very, very simple.
Okay, so let's give a big hand to Boris.
Okay.
So as Boris indicated, so they have a demonstration here, so please feel free to interact with them throughout the workshop. So we'll take a short break for 30 minutes. But before that, a short announcement. I think I sent a note to all of you in-person attendees. So if you have any meetings to take a call or something, just we have 2 other conference rooms reserved.